Hello, statistical scholars, and welcome to our first in many fun adventures in probability. So what I'm going to talk to you about today is what we call a cross-tabulation, a two-way table, or a contingency table. Now, this should look familiar from the days when we talked in the beginning of the semester about marginals, if that sounds familiar, I hope. And we had talked about how, if I want to look at the marginal distribution of a particular variable, then I just need to look on the margins, like so. So this data in particular represents the 100 senators from the 112th U.S. Congress in 2011 on a specific date. So we have two variables that are interacting with each other. We have political party affiliation and then gender. So we're going to talk about what it's going to be like to select a random member from this group, given that this is its distribution. This is what it looks like. These counts specifically tell us how many of each of these we see. So this square in particular, the 39 square, represents the number of people that had the value of Democrat for their political affiliation and male for their political affiliation. So as you look along these squares in the middle that are non-bolded, they represent ands, so people that have both. Whereas if you look down a row, so Democrat, and look at its total, this is just the value or the total count of the number of Democrats present. I hope you get the idea here. So like we said, if you wanted a marginal distribution, when we looked at marginals, we would ignore the other variable and pay attention to the totals to figure out the distribution for the political variable. Or down the columns, you could do the column marginal, and you would be knowing political affiliation and just looking at gender, so 83 males and 17 females. And as you look at this, keep in mind that, if you ever get rows and columns confused, this is what I was going to tell you. Remember, think columns like you see in Roman columns in architecture. They go up and down, and then rows, you go like down your rows to, seat yourself at the auditorium. They're usually parallel like this. Okay, so let's first look at what's the probability that a senator is female. And I'm just going to write this as a probability statement to get you a little used to those. So in particular, if I look at how down the marginal for female, that would be 17 out of 100 females, which you could write as a decimal. Sorry, 0.17. Either or. Remember that usually probabilities we list as proportions or decimals between 1 and 0. We do not list them as percentages. Occasionally questions will ask you for a percentage, but in general we don't write that the fraction is equal to the percentage because it's simply not true. If you wanted to write this as a percentage, you properly should write or 17%. Don't write that they're equal because it's absolutely not true. All right, now let's look at what's the probability that a senator is a Republican. Should have chose independent, that way it was, a little less politically volatile. Haha. Okay, so the probability that you're a Republican, we'd be looking down the marginals on the rows and looking at the probability that you're Republican, so that was 51 out of the total of 100. So also, as you pay attention to this, really think about the number that we're putting on top of the probability is the number for the event I'm interested in out of the total that's present, okay? Now, this is a little bit of a different statement. Oh, that's italicized. Let me fix that real quick. Okay. I don't know why this looks different. So I'm interested in the probability that they're female or Republican. That came out weird. All right. So here you have to be a little bit more careful because there's a lot going on here. I want to count for my numerators all of my females, all of my Republicans, and not count any overlap. So you have to be careful here. So typically we would do this using that formula for ORs, which is to find the probability that we're female plus the probability that we're Republican, because we want to count all of them. But you have to be careful. So if I were to count all the females and all the Republicans, which is what this plus is, I wouldn't be correct, because if you're female or Republican, you might be in both of these groups, which would be the and situation. I can't spell. So look at this. So Democrats, sorry, Republicans. You count how many Republicans there are. Oh, there's 47. You count how many females there are. Oh, there's 17. But if you're a female who's also a Republican, we just overcounted you because you got counted in the Republican group and the female group. So we counted you both. We need to subtract. So I want to subtract the females that are also Republican. This isn't going to fit now that I made it bigger. Sorry, I'm just going to take 2 seconds to make this smaller. Some of these videos are not very fast. Okay. So to figure this out, female I found 2 seconds ago. That's 17 out of 100. Republican I found 2 seconds ago. That's 51 out of 100. And I'm going to subtract from that the people that I'm overcounting, so the 5 out of 100. So if you look at my answer key, I wrote these as all one fraction since they all have the same denominator. You can do that. So that's 59 out of 100 people, or 0.59. Lovely. Okay, so let's look at being a senator and male. So I'm looking for 2 of them together. Male and Democrat. Woo! I'm always tempted to put an E at the end of Democrat. It's like Democrat. Fun times. So male and Democrat, that's what I was talking about earlier. That's just the entry in this column to count the number, and I'm doing it out of all possible senators. Okay. Now here's where things get a little hinky in E and F. So I want to find the probability that I've picked a Republican. Given that I already know that this person is female. So this is a different situation than what we were doing before. So A through D was all about, hey, I'm looking at all possible peoples. What am I drawing? And this is, I've already drawn a female. How likely is it that it's a Republican? So I know more information than I did before. So I look at, you know, all of my females, because I already know I've drawn a female. So my total is now the 17 I'm dealing with. And of those, only 5 are Republican. So 5 out of 17. Hopefully that made sense to you. Now, you can do this another way using the formula given to you about conditional probabilities in your book, which is look at the intersection, divide by the group of size that you're interested in. If you want to see that really quick, that would be probability Republican whatever given female. I should have just done letters like F for female, R for Republican, since none of these are the same. That would have been faster. So I gotta find the probability I'm Republican and female, and then divide it by the probability that you were female, which you easily could do. It comes out exact same as the other calculation. So if you want to add some more steps to this and use the actual physical definition, that's how you would do it. That's probably going to drive some of you crazy. Sorry, it thinks this is one word. That's funny to me. Terrible giggles. Done. Okay, so probability that the senator is male, given he's a Democrat. So notice I'm doing the conditional now on, oh, I know they're a Democrat. Is it likely that they are a gentleman? So I look at only the Democrats, so my total is out of 51, and consider the males. So 39 out of 51. Or I'd rather say I'm interested in, are they male? Oh, I forgot to write the decimal for the other one, but I'm going to round this 765-ish. Okay, let's go to our second example. So this one is looking at a baseball clinic amongst, you know, high school and college students with different positions, and looking at where they're at. So some probabilities to find there. So we're selecting one player at random and asking, how likely is it that they're this? So if I want to find the probability that they're an infielder, I would take my total for the infielders and divide it by my total number present, which is 100. The probability that they're not in college, so I'd be considering only the junior highs and seniors, so 30 plus 32 divided by 100, which would give you 62 out of 100. Doing this a little faster, sorry. If I want to look at high school and a catcher, that's an intersection. That's going to be just inside the square. So high school and catcher, where is it? Oh, 4 out of all of them, so 100, because there's no given here. It's very easy to confuse the ands with the givens. It's not that I'm only considering high school seniors or only considering catchers. I don't have one already. It's not given that they already were a catcher. It's I want to know what's the likelihood that I get both of these behaviors. Okay, so junior high school or a pitcher, so I gotta be careful here. I gotta count the or, so I gotta make sure I don't overcount. I'm gonna use parentheses for this one. Wilson. Oh, I don't like how that lined up. Excuse me. So I want junior high school, that's a total of 30, plus pitchers, that's a total of 15, and then I gotta subtract the intersection of 4, and then divide that by my total. Since I'm considering all, it's not a conditional. So here that'd be 41 out of 100, which you could calculate the decimal for. Whoa, well that I didn't see coming. Why is this highlighted? That's insanity. There, okay, sorry, took care of that. Okay, it didn't take care of that, whatever. We're gonna have a green line for no reason. So, this is another OR situation, so I'm gonna count the outfielders, or students that are in college, and then, you know, subtract the intersection. So 35 plus 38 minus the ones they have in common, which is a 14. Take that and divide it by 100. I don't know if this is the most interesting in the world. So that would be 81 out of 100. Bright green, so pretty. So pretty. Sorry. My weird is showing. Okay, so now we're only considering outfielders and asking how many of them are in college. So what's the likelihood that they're in college given that they're an outfielder? So looking at the outfielders, there's 35 of them, 14 are in college, so it's 14 out of 35. Now, given that I'm dealing with a junior high student, what's the likelihood that they're a catcher? So be careful how you read these. Read them out loud to yourselves a couple times to the point where you'll read them in your head correctly. It does help. So the probability that I've drawn a catcher, given that they're in junior high. So I already know they're a junior high student. How likely is it they're a catcher? So let's see, junior high is 30, out of which 6 are catchers, so 6 out of 30. All right, here's a fun question. So if I'm going to draw 2 players selected with replacement, so remember with replacement means after I've drawn that person, I let them go back in, so I'm not going to have like them stand there where I draw a second person. I want to find the probability that both of them are in college. So in looking at this, I'm going to draw one player and then draw another. And the likelihood that you're in college, we didn't calculate earlier, but that's okay. I should have designed this a little bit better. 38 out of 100 of mine are in college, and 38 out of 100 of mine are in college, so we'll multiply those together, which gives you, about 0.444. I'm rounding with that one. So the difference between H and I is that you have to imagine, like, I drew out 2 players, but I'm drawing them one at a time, and after I've drawn the first one, I put it back in. So it's a little bit like drawing cards and then either keeping it in your hand or not keeping it in your hand. It is a slightly different scenario. So on my first draw, I have, 38 of them that are in college out of 100. And on my second draw, I have 1 fewer person there. So it's out of 99 people and 1 fewer person that's in college. There are 37 of them. So that's slightly different. And that's a 0.1420. So notice that's slightly smaller. It's a little bit less likely. Kind of fun? Maybe, maybe not. All right, let's look at this last one. So if 2 players are selected at random without replacement, find the probability that the first player is a pitcher and the second player is an outfielder. So I'm going to be careful about this. I have 100 players in the first fraction and only 99 in the second one. So I have 1 less person, so I'm being careful. In the first one, I need to be a pitcher, so I got to ask myself, how many pitchers are there? There's 15 of them, okay, 15 pitchers. And then I need an outfielder after that. And luckily, I can do it this way. So the big thing going on here is that these 2 events, pitcher and outfielder, are independent. There's nobody who can play both those positions. Well, maybe you can, but you don't play them at the same time at the same game, or probably in the same practice. I don't really know that enough about baseball to say that that's even true. Wow, crazy lady. Gotta choose a different example next time. But the big difference is, hopefully you notice that H and I, since I'm drawing the same thing twice, the in college attribute that I'm interested in, the probability changes, which should tell you that sampling with replacement and without replacement are not independent. Or another way to think about that is if I sample without replacement, my second event's probability changes based on what I draw first, therefore these are not independent events. Since these are independent, I can just multiply them. Alrighty, that is all. I gotta figure out how to pause this now. There it is. Peace out, homies.